Hello guys, welcome on Tesla Adventures. In this video, we are starting the thermodynamics and let us discuss. In fact, we have already started the thermodynamics, but in this video, we are going to discuss the laws of thermodynamics. In fact, from today, from this video, we are going to discuss the laws of thermodynamics and all the processes like adiabatic, isothermal, etc. So let us first of all understand that what do thermodynamics tells us about the heat. So as you can see that it is the branch of physics which in fact there is a common misconception and debate going around in the students that whether thermodynamics is the branch of physics or chemistry. Most of the physics teacher says that it is the branch of physics, and most of the chemistry teacher says that it is the branch of chemistry. But the fact is that thermodynamics is the branch of physics, and this is the fact because in chemistry thermodynamics was introduced to understand some basic chemical reactions of the gases and other elements which are based on the heat exchanges. So thermodynamics was introduced in chemistry, but actually the thermodynamics is the branch of physics, or to end up the discussion you can say that thermodynamics is the branch of science. Okay. So it deals with the conversion of one form of energy into another form. What its name suggests, that thermo plus dynamics, you can say that thermodynamics is the study of converting the heat energy into work done or mechanical motion. Okay, now you can easily see, or you can easily see around you that in cars or supercars there is a powerful engine, and that powerful engine is converting the energy stored in the fuel into mechanical work. So that is the car engine is a thermodynamical engine which converts the energy from one form to work done. Now thermodynamics also deals with the macroscopic state variables of the system, such that temperature, pressure, volume and number of moles, instead of microscopic state variables such that position, velocity and force of the molecules of the gas. So it is very important that we are not concerned widely with the microscopic variables in the thermodynamics. In fact, we would always denote the state of any thermodynamical system by the macroscopic variables like pressure, volume, temperature, number of molecules and internal energy and entropy. So these are the major state variables which we would use to describe a thermodynamical system. Now let us first of all discuss the differences between thermal and thermodynamical equilibrium. So you can see that this is a chamber which has a conducting partition, and this partition allows the slow transfer of heat through it, and there are two gases A and B. So this gas A and B are in thermal equilibrium, which means that the temperature of gas A and temperature of gas B is same, and it does not means that there is no heat exchange going on between the gases. In fact, there is a continuous exchange of heat going on between the gases, but we can say that the rate at which gas A is giving the heat to gas B and the rate at which gas B is giving the heat to gas A is equal, and therefore we can say that the net transfer of heat in any of the direction is zero. So this system is said to be in thermal equilibrium, and we can also say that in thermal equilibrium the state variables are constant. See, this is a very important, very important aspect of thermodynamics, that in thermodynamics we always consider that during the transition of gas from one temperature to another temperature also, we assume that transition is occurring so slowly, so that the gas is always in thermal equilibrium and all of its state variables are constant at any moment of time. Now I'll tell you a practical example of this fact, that whenever we move a block very slowly with a constant and negligible speed, then we can say that although block is moving from one position to another position, but the block is in in fact the block is in mechanical equilibrium always, because the net force acting on the block is zero, because its velocity is constant at all the moments of time. This is the exactly relatable fact in thermodynamics, that whenever a gas is transiting from one state to another state in thermodynamics, we always assume that the transition is so steady and so slow, so that at each moment of time all the variables of that gas are constant at each moment. And these type of processes are called as quasi-static process. I will make a separate video on the quasi-static process later, but let me tell you another example, that have you noticed any child growing up? So at any moment of time you would not notice his growth, because at any moment of time he would seems to be steady. He would not be growing too fast at any moment of time. So you could not see that child growing instantaneously. But eventually, after some time, when you will notice, in fact after some months or some years, when you will notice the child again, you will see his height to be increased, but obviously you cannot see instantaneously that his height is increasing. So this is a very slow process, and at any instant of time the growth of the child is in equilibrium. Okay, so there is no accelerated growth of the child. So this is also the example of a quasi-static process, and this is the thermal equilibrium. So very important thing which is to note in this thermal equilibrium part is the fact that a system will be in thermal equilibrium if its state variables are constant at any moment of time. Now let us discuss the thermodynamical equilibrium. Let us consider that there are two gases A and B, you can see, which are inside this chamber, and this chamber is isolated from the surroundings, and there is no method of heat exchange between the gas and the surroundings. So this piston has a small hole in it, and this piston is conducting piston, and in fact it is also movable piston. Now what we are observing is the fact that these gases are reactable, but then also their concentration is fixed, they are not changing. So we can say that they are having a chemical equilibrium state, and the temperature of these two gases is also same. So we can say that the gases are in thermal equilibrium state, and this piston is not moving, which means that the gases are in mechanical equilibrium also, because net force on the piston is zero. So if these three equilibriums coexist between the two gases, thermal equilibrium in which temperature of the gases is same, chemical equilibrium in which concentration is constant, and mechanical equilibrium in which pressure of the gases is same, then these gases are said to be in the state of thermodynamical equilibrium. So actually thermodynamical equilibrium is the combination of three equilibriums: thermal, mechanical and chemical, and thermal equilibrium is separate one. So if a system is in thermal equilibrium, we could not definitely say that it would be in thermodynamical equilibrium also. But if a system is in thermodynamical equilibrium, we could definitely say that it would be in thermal equilibrium also. So I hope that in this video you got the basics of thermodynamics quasi-static process, on which I would be making a separate video in the later part of this playlist, and the differences between the thermal and equilibrium and the thermodynamical equilibrium. In next video, I would be bringing some concepts about gas, vapor and humidity. Thank you.